Hello and welcome to our lesson on calculating bond energies. This is for higher tier students only. Let's go. Okay, so the first thing we need to recognise is that all reactions are both endothermic and exothermic. Now I've blown your mind, let me explain why. So every reaction needs to break existing bonds. So they're going to require some extra energy to do so. So they're going to take in some energy from the environment, endothermic, to break any existing bonds. When it makes new bonds, it releases some of that energy. And so the product side is always exothermic. So with any complete chemical reaction, we break existing bonds, endothermic, and we make new bonds, exothermic. So we can say then reactants are always breaking bonds. There we go, endothermic, and products are always making bonds, which is exothermic. And any chemical reaction will do both of these things and therefore are both endothermic and exothermic. Here's your first core concept for today. Endothermic, exothermic. Now, make sure you get these the right way around. It's in and then out, not out and then in. So if all reactions are endothermic and exothermic, why do we say photosynthesis is endothermic and respiration is exothermic? Well, it comes down to a comparison between the amount of energy needed to break the existing bonds and the energy needed to make new bonds. So you can imagine if it's going to take more energy to break them, which is endothermic, than it would to remake it, overall it will be an endothermic reaction and vice versa. So let's have a look at this in a bit more detail. Okay, so we have a chemical reaction here. Propane, which is a hydrocarbon fuel, added to oxygen. So we have a combustion reaction, making carbon dioxide and water. And I've given you some numbers here. So the bond energy needed to break these bonds is 6,522 joules per mole. And this is taking in that energy, endothermic. Okay, so it's taking in 6,522 kilojoules per mole. When it makes new bonds, it's releasing any extra energy, and it's actually releasing 6,912 kilojoules per mole. So does this reaction take in or give out more energy overall? Well, hopefully you'd recognise it's actually giving out more energy than it's taking in. There you go. It's minus, if I take away, so 6,522 minus 6,912, I've got a negative number, so minus 390 kilojoules per mole. So is it endothermic or is it exothermic? Well, it's an exothermic reaction, isn't it? Because it's giving out more energy than it's taking in. So what would happen to the temperature? Well, if it's an exothermic reaction, the temperature would increase. So right now, the one thing that might be confusing you is that minus number. It's really, really important that when you do these calculations, you take away the reactants minus products. And if you end up with a minus number, that minus means it's an exothermic reaction because it's releasing the energy. It's less energy than it was. So the core concept then, when calculating bond energies, always do reactants minus products. And if you get to the negative number, it means you have an exothermic reaction. Okay, so pause the video for me and have a go at this for yourself, please. Okay, so lithium plus oxygen, making lithium oxide. So it says label the bond energies. So we have endothermic on the reactant side and we have exothermic on the product side. Okay, it says calculate the overall bond energies. So you do 1,300 minus 1,450, giving you minus 150 kilojoules per mole. So what type of reaction is it? Well, it's a negative number, so it's exothermic. So what would happen to the temperature? Well, hopefully you would remember that the temperature would increase because it always does with an exothermic reaction. Okay, so now you've got that straight in your head, let's go a bit deeper. Where do these numbers actually come from? Well, they come from the bonds. let's look at this example here. So on the left reactant side, I am breaking 2 lots of hydrogen bonds. So we know from chemistry, from experiments, that a hydrogen bond requires 440 kilojoules per mole energy to break them. And I've got 2 of those. And then I've got 1 double oxygen bond. I know it takes 498 kilojoules per mole to break that bond. That gives me, if I add those together, a total bond energy needed on the reactant side, 1,378 kilojoules per mole. On the product side, I've got 4 OH bonds. And I know each one of those is 464, so I've got 4 lots of those. Now, where have I got 4 from? This is where people get confused. That there is 1, and then that there is the second. Doesn't matter that I've got 1 oxygen, that there is the bond. So I've got 1 bond there, 1 bond there, another bond here, and another bond there. So 4 times 4 gives me the bond energy needed on that side, 1,856. If I do the calculation, I end up with minus 478 kilojoules per mole, which means it's an exothermic reaction. You do not need to know these numbers. You will be given these numbers in the exam. It's just up to you to recognise how many you've got. Okay, so different bonds need different amounts of energy. Like I say, you don't need to know this by heart, but this is where people trip up, and it is practice makes perfect on this, guys. My apologies, it's just the long way around. But H2 is 2 H's bonded together, so that's a single bond there, 440 kilojoules per mole. O2, that's actually a double bond. That would be 140, for example. CH, 410. What about this? I've got 2 lots of N2, so actually something like this. So I'd have double what I would normally have, which would be 4. So each of them is 420. So 2 of them together will be 840. And again, it's just recognizing what you're looking at, and there is no shortcut to this. It is just getting your head around it and having a practice. Okay, so if you're confident, have a go at this question for me. Okay, so in this calculation then, I have got 1 lot of HH, so that's 440. I've got 1 lot of ClCl, which is 239, which gives me a total here of 679 kilojoules per mole. On the product side, I've got 2 lots of the HCl, so that's 427 and 427, giving me a total of 854 kilojoules per mole, which gives me a grand total of minus 175 kilojoules per mole, and that is going to be an exothermic reaction. Okay, have a go at this question for me. The table is at the bottom right. Okay, so here I have, on the reactant side, I have 1 hydrogen to hydrogen bond, which is 440. I have 1 fluorine to fluorine bond, which is 142. Added this together, I've got 552 kilojoules per mole. On the product side, I've got 2 lots of the H to F, the hydrogen to fluorine bond. So that's 568 times 2, 1,136. I do that calculation, 552 minus the 1,136, giving me an energy change or an enthalpy change of minus 584 kilojoules per mole. And again, this reaction is exothermic. Okay, pause the video and have a go at this question for me. Okay, so this is a little bit different because we don't have it written down. We have that displayed formula, but it's exactly the same idea. So let's have a look. So on the reactant side, I've got some carbon to hydrogen bonds, haven't I? Or hydrogen to carbon bonds, which way you want to look at it. And how many have I got? I've got 1, 2, 3, 4 hydrogen to carbon bonds. So that's 4 lots of 413. So that's 1,652. Okay, and then I've got 1 chlorine to chlorine bond, chlorine to chlorine, which is 243. Okay, and that's it on the reactant side. So add those together, I've got 1,895 kilojoules per mole. Okay, on the product side, at first glance, that looks exactly the same, but it's not. Okay, so be careful, we've got a chlorine to carbon bond there. So we've got 1, 2, 3 hydrogen to carbon bonds. So that's 1,239. I've got 1 carbon to chlorine bond, carbon to chlorine, which is here, 327. And I've got 1 hydrogen to chlorine bond, which is 432. Okay, do that equation. So there you are, 1,998 added together. Okay, so then we take reactants from products, giving us minus 103 kilojoules per mole. And that was the question, wasn't it? It says show enthalpy change. Okay, and that triangle there means change in enthalpy or change in energy. It's telling you it should be 103, minus 103, so you know what you're looking for. And bish bash boom, we've got the job done. Okay, that's it for today, guys. See you later.